September 27, 1941. Bethlehem Fairfield Shipyard, Baltimore, Maryland. Welders worked beneath the steel frame of a new type of cargo vessel. The ship measured 441 feet in length and 57 feet in beam. Rivets were absent. Welds replaced them along every seam and joint. Nearby, naval inspectors recorded test data for structural integrity and hull vibration. The hull number read Liberty Ship, SS Patrick Henry. The project originated under the United States Maritime Commission. It aimed to mass-produce cargo ships for emergency wartime supply needs. Henry J. Kaiser, an industrial contractor, managed the shipyard's construction schedule. The ship's design came from a British concept adapted by American naval engineers. Chief among them was William Francis Gibbs, but the simplified plan was revised further. It was assigned to naval architect Edward L. Cochrane and later standardized by Andrew Higgins design engineers. The objective: build a cargo vessel faster than any in recorded history. Each section of the hull was pre-assembled inland and transported by rail. Foremen marked each component with stenciled numbers for rapid alignment. Cranes lowered modular units onto the keel within hours. Observers compared the process to toy construction models due to its simplicity. By October, the nickname "the ship that looks like a box" spread among naval contractors. Shipbuilders and dockyard engineers mocked its blocky appearance and welded seams. Official records show the initial build required 244 days. Compared to earlier standards, this duration was already half the usual time. The SS Patrick Henry launched on September 27, 1941, before an audience of 30,000. President Franklin D. Roosevelt delivered a radio address marking the occasion. He stated, "She will bring liberty to Europe." From this phrase, the Liberty Ship name entered official usage. Observers noted its specifications. Deadweight tonnage, 10,856 tons. Cargo capacity, 9,000 tons. Engine, triple expansion, 2,500 horsepower, capable of 11 knots. Crew complement, 41 officers and men. These figures were published in the Maritime Commission Technical Report No. 173-A, 1942. Journalists described the launch as a test of America's industrial mobilization. Across the pier, additional keel blocks had already been laid for future hulls. Each bay was designed to assemble one Liberty ship every 2 weeks. Blueprints were standardized across 18 American shipyards under commission control. Government observers from the War Production Board recorded the data for assessment. The Liberty ship's welded hull represented a major deviation from naval tradition. Riveted joints, long considered essential for ocean-going durability, were replaced by arc welding. This change reduced weight and shortened build time by approximately 25%. Engineers from the American Bureau of Shipping inspected each weld using X-ray imaging. By the end of 1941, production efficiency metrics improved by 12% per vessel. The SS Patrick Henry completed sea trials off Chesapeake Bay on November 30th. Performance met all specifications under calm weather testing. Recorded stress tests confirmed hull stability under a 9,000-ton load. The vessel was declared seaworthy and transferred to the War Shipping Administration. Within days, the Maritime Commission issued new directives to replicate the process nationwide. By the close of 1941, 7 Liberty ships were under construction simultaneously. Each shared identical modular plans, pre-numbered components, and standardized machinery. The system was designed to eliminate bottlenecks and human error. It would soon produce ships faster than any shipyard had previously imagined. By early 1942, the United States faced a maritime crisis. German U-boats were destroying Allied shipping faster than it could be replaced. Between January and June, 397 merchant vessels were sunk in the Atlantic. Cargo losses exceeded 2.5 million tons. Military planners concluded that supply attrition, not combat, posed the greatest threat to Allied operations. The United States Maritime Commission accelerated emergency shipbuilding contracts. 18 shipyards received authorization to begin Liberty ship production under a unified schedule. The plan relied on mass production methods previously unused in naval construction. Industrial engineers applied automotive assembly principles to ship fabrication. Each yard divided the vessel into 250 prefabricated sections. These were built concurrently by independent subcontractors across the country. The shipyards at Richmond, Portland, and South Portland became the primary production sites. At Richmond, Henry J. Kaiser's management approach emphasized speed over tradition. His workers operated around the clock in 3 shifts. Each stage of the assembly process was measured in man-hours, not calendar days. The Kaiser system reduced construction time to under 50 days by mid-1942. Official Maritime Commission data shows an exponential increase in output. In January 1942, one Liberty ship was launched every 23 days. By December, one launched every 6 days. The average labor time dropped from 1.4 million man-hours to fewer than 500,000. These records were verified by the Bureau of Labor Statistics in War Production Bulletin 227, 1943. Most of the ships followed the EC2 SC1 design standard. This designation signified an emergency cargo vessel, Type 2, steam propulsion, Configuration 1. Each unit carried 5 cargo holds, 1 3-inch bow gun, and 1 4-inch stern gun. Anti-aircraft armament varied by convoy assignment. The ship's engine, an oil-fired, triple-expansion reciprocating type, was simple and reliable. It could be built domestically without advanced machine tools. Critics in the U.S. Navy called the Liberty ship an ugly duckling. They argued that the hull's flat sections produced excessive drag and poor maneuverability. Ship captains complained of vibration, noise, and low cruising speed. However, cargo officers valued its predictable handling and large storage capacity. Operational records from 1942 to 1943 show 95% of Liberty ship deliveries reached destination ports successfully. The modular design was developed by naval architect Henry J. Kaiser's team, led by Howard Love. Their approach emphasized interchangeability of parts between yards. A hull section built in Maine could fit precisely into one built in California. This precision came from standardized blueprints distributed by the Maritime Commission. All measurements used uniform templates derived from British Sloan-class freighters. The Americans, however, replaced rivets with welds, saving over 300,000 pounds of steel per ship. By March 1942, the War Shipping Administration began to reclassify Liberty ships for specialized use. Variants were built as tankers, hospital ships, and troop transports. Others served as ammunition carriers or floating workshops. This adaptability reflected the underlying modular philosophy of the design. Each vessel shared a common structural grid, allowing internal reconfiguration within weeks. The program required new labor forces. Women and untrained civilians entered the shipyards in unprecedented numbers. They were trained within 2 weeks to handle welding, riveting, or crane operation. Records from the Richmond Yard list 38% of workers as female by mid-1943. Production manuals were rewritten in simplified language to accommodate new labor demographics. This marked a shift from skilled craftsmanship to procedural engineering. By the summer of 1942, the United States had turned shipbuilding into industrial routine. Every new hull marked not an achievement, but a scheduled output. The Liberty ship ceased to be a prototype. It became an industrial product, identical, replaceable, and measurable. By late 1942, production engineers began documenting lessons from early Liberty ship operations. The first 60 vessels had revealed patterns of structural fatigue and material stress. Investigations by the United States Maritime Commission recorded fractures near the deckhouse and midship seams. These failures occurred under Arctic convoy conditions, where temperature dropped below -20 degrees Celsius. Welded joints contracted unevenly, producing brittle cracks across the steel plate. Metallurgical studies were conducted at the University of California and the Bureau of Ships Laboratory. Tests identified the cause as knot sensitivity in low-temperature steel. The defect originated from wartime steel substitution to accelerate production. Instead of nickel steel, most yards used plain carbon-manganese alloys. Although easier to weld, they lacked elasticity in freezing environments. The Commission issued Technical Bulletin 243 in January 1943. It ordered reinforcement of deck and hull seams using additional fillet welds. Inspection intervals were standardized across all 18 shipyards. X-ray and magnetic particle testing became mandatory on main hull joints. This improved reliability metrics by 14% within 6 months. At the same time, yard supervisors tracked production time per unit. Statistical charts showed a downward curve in average build duration. By May 1943, the median construction period dropped below 40 days. Kaiser's Richmond Yard No. 2 achieved a record, the SS Robert E. Perry built in 4 days, 15 hours, and 29 minutes. The record was verified by Maritime Commission observers on site. The accomplishment was not symbolic, it proved the modular principle's viability. Each prefabricated section was delivered pre-assembled from inland plants. Workers bolted and welded them under continuous lighting, using standardized jigs. Blueprint overlays confirmed perfect dimensional conformity between parts. The process demonstrated that a cargo ship could be built like an industrial product, not a craft. Reports from the British Admiralty noted the same observation. In a memo dated July 1943, British naval attachés described Liberty ship output as unprecedented in maritime history. They recorded over 800 Liberty ships launched in that year alone. The Royal Navy allocated many under Lend-Lease for convoy supply routes to Murmansk and Alexandria. Operational data confirmed an average survival rate of 87% per voyage, comparable to any British-built freighter. Industrial scientists analyzed the psychological impact of scale on efficiency. Production rate improved as each yard reached a steady-state workflow. Once assembly lines were synchronized, human labor followed machine pacing. Workers specialized in single tasks, welding, fitting, or testing, without direct knowledge of the full vessel. The approach reduced training time but increased precision consistency. In Portland, Oregon, engineers implemented a rotating component schedule. Hull sections, decks, and bulkheads arrived at the slipway in a fixed sequence. Each component carried an identification plate coded by lot and date. This made defect tracing immediate and simplified inspection reporting. By the third quarter of 1943, defective weld percentages fell below 2.8% nationwide. Shipyards coordinated through the Maritime Commission Central Production Office in Washington, D.C. Weekly teletypes reported ship completions, man-hour efficiency, and material shortages. Charts published in Shipyard Review indicated the industrial curve approaching asymptotic speed limits. Output was now limited not by skill, but by material logistics and weather. That the discovery phase of Liberty shipbuilding was complete, efficiency itself had become the weapon. By the end of 1943, 1,146 Liberty ships had been launched. The system had stabilized into a reproducible cycle measurable in days, not months. From blueprint to ocean service, every action followed recorded procedure. The toy-like design was no longer a curiosity. It had become the foundation of the largest shipbuilding campaign in human history. By early 1944, the Liberty ship had become the backbone of Allied maritime logistics. Production reports listed 2,500 hulls completed or under assembly across 16 American shipyards. Every ocean route, from the Atlantic to the Indian Ocean, relied on these vessels for supply continuity. Convoy manifests showed Liberty ships carrying food, tanks, aircraft parts, and medical supplies. The scale of transport surpassed any logistical effort previously recorded in naval history. The War Shipping Administration analyzed data from 1942 to 1944. Findings confirmed that over 70% of Allied cargo tonnage was delivered aboard Liberty ships. This transformation occurred in less than 3 years. Industrial historians later classified it as a turning point in wartime supply engineering. The design once dismissed as crude had proven decisive through scale and reliability. Naval reports emphasized that no other ship type could be produced as rapidly. Welded construction eliminated dependence on riveters, who remained in short supply. Prefabrication allowed inland factories to contribute without access to the sea. Entire ship sections traveled by rail to coastal assembly yards. This integration of inland and maritime industry became a model for total war production. By April 1944, the Maritime Commission introduced incremental upgrades. Reinforced Victory ships entered testing, featuring improved hull lines and more powerful engines. Yet the Liberty ship remained dominant, with orders continuing through mid-1945. Its simple machinery required minimal maintenance, allowing quick crew training and field repair. For every ship lost, another was completed within days. Statistics compiled by the Bureau of Ships demonstrate the operational endurance of the type. Average Liberty ship service life exceeded for years during wartime conditions. The standard engine ran 16,000 hours before overhaul. Fuel consumption averaged 30 barrels per day, lower than equivalent foreign freighters. These quantitative advantages outweigh design imperfections. Engineers at the Richmond and Portland yards reached a collective realization. The Liberty ship was not a naval experiment but an industrial system. Blueprints, workforce management, and material logistics formed an inseparable production network. It functioned independently of geography or local skill. Each shipyard became a node in a single national assembly line. Reports from naval intelligence confirmed enemy recognition of the achievement. German assessments captured after the war described an unbroken stream of replacement tonnage. Japanese naval officers noted that American transport losses were restored faster than sunk. Axis strategy documents from 1944 refer to the factor-a-fleet concept, derived from Liberty production data. These records reveal how mass production altered enemy planning assumptions. The Liberty Ship program also redefined American industrial identity. Before 1941, shipbuilding was an artisanal process requiring specialized labor. By 1944, it had evolved into an automated operation driven by mechanical precision. Assembly line methods spread to aircraft and vehicle production facilities. Welding technology, first standardized on the Liberty hull, became standard across post-war industries. Shipyard bulletins show a decline in average age of workers by mid-1944. Many were under 25, trained directly on the line. Productivity remained high due to the simplified task segmentation. The experience transformed thousands of civilians into skilled technicians. Their expertise later fueled post-war reconstruction and peacetime manufacturing. By the end of 1944, the United States had produced more cargo ships than all Axis nations combined. This output was not symbolic, it was the operational expression of industrial warfare. Each vessel represented a logistical constant, predictable, measurable, and reproducible. The Liberty ship had validated the principle of total industrial mobilization. The toy had become the template for a modern war machine. By January 1945, Liberty ship production entered its final, most efficient phase. Records from the United States Maritime Commission listed 2,710 completed vessels. This figure represented a combined carrying capacity of over 30 million deadweight tons. In practical terms, it equaled the movement of 200,000 tanks or 3 million tons of ammunition per month. The Liberty ship had become an arithmetic component of Allied strategy. The program's coordination model became the template for post-war logistics systems. Each shipyard communicated through the Commission's centralized teletype reporting network. Daily output figures were broadcast to Washington, San Francisco, and London. Production delays were flagged automatically and reassigned between yards. This early data network resembled later industrial computing principles. The shipyards themselves became research centers for industrial organization. Harvard Business School and MIT industrial management teams documented workflow and human factors. They observed a direct correlation between standardization and output stability. Variation control, not labor increase, became the dominant production strategy. Efficiency depended on uniformity across thousands of independent workers. At peak operation, the program employed more than 600,000 workers nationwide. They were distributed across coastal yards, inland steel plants, and transport depots. Civilian training schools taught welding, blueprint reading, and arc inspection. Instruction manuals, issued by the Maritime Commission, used visual symbols instead of technical jargon. These procedures ensured identical performance regardless of education level or regional background. From a strategic standpoint, Liberty ship logistics redefined Allied naval capability. Each convoy contained ships built in multiple states, assembled from shared components. This interchangeability simplified repair, refit, and spare part distribution overseas. Naval depots in Britain and Australia stocked standardized replacement panels and machinery. Operational downtime for damaged vessels decreased by over 40% between 1943 and 1945. The British Ministry of War Transport integrated Liberty ships into transatlantic convoy schedules. Out of 2,710 hulls, 722 served under the British flag through Lend-Lease. They carried war material to North Africa, Italy, and the Soviet Union. Many made the Arctic run to Murmansk under extreme conditions. Reports indicated that over 150 were lost to submarines, but replacements arrived before the month's end. In the Pacific Theater, Liberty ships provided uninterrupted supply to island operations. Each carried aviation fuel, artillery, and rations to forward bases. Unlike specialized vessels, they could unload at unprepared beaches using temporary cranes. Commanders valued their ability to self-sustain convoy throughput. The design stability allowed precise cargo stacking, reducing loading time by half. Statistical evaluation by the War Production Board showed the program's macroeconomic impact. Liberty ship construction accounted for 1/5 of total U.S. wartime industrial output. Steel allocation, labor utilization, and logistic efficiency metrics all peaked in 1944. The average cost per ship fell from $1.9 million to $1.6 million despite inflation. This demonstrated scalability without loss of unit consistency. Economic analysts concluded that shipbuilding no longer depended on craftsmanship or tradition. It was now a mathematical process defined by timing, flow, and replication. This transformation influenced subsequent American industries, automotive, civil engineering, and aerospace. The Liberty ship thus represented not only maritime strength but industrial philosophy. Production became a form of strategy equal in importance to combat deployment. By the spring of 1945, as Europe neared liberation, Liberty ships dominated every convoy list. They were not celebrated as individual vessels but as operational constants. Each hull carried a numerical designation, its identity secondary to its purpose. The program's success proved that victory could be constructed, scheduled, and shipped. The Liberty ship had converted American industry into a synchronized wartime engine. By August 1945, the war in the Pacific had ended. American shipyards received orders to cease Liberty ship construction by mid-September. At that point, 2,710 hulls had been delivered, crewed, and deployed worldwide. No other ship class in maritime history had reached that quantity in so brief a span. The Liberty ship stood as a quantitative expression of total industrial mobilization. Post-war assessments conducted by the U.S. Maritime Commission began immediately. Teams inspected surviving ships for wear, corrosion, and fatigue. Most remained serviceable after more than 3 years of continuous operation. Reports from Maritime Administration Bulletin No. 312, 1946, confirmed hull integrity above expected limits. Despite known issues of brittle steel, only a small fraction suffered critical failure. Many Liberty ships were retained for peacetime commerce. They carried grain, coal, and construction materials to Europe and Asia. Under the Marshall Plan, several hundred were converted into civilian freighters. Others were transferred to foreign registries as part of reconstruction aid. By 1948, over 900 Liberty ships operated under non-U.S. flags. Shipyard closures followed rapidly. Temporary wartime yards at Richmond, South Portland, and Brunswick were dismantled. Welding equipment and cranes were sold to private contractors. The trained labor force dispersed into civilian industry. Their experience directly influenced the emergence of post-war steel fabrication and petrochemical plant construction. In 1947, the War Department Industrial Review Board published a comprehensive report. It classified Liberty ship production as a model for systemized manufacturing. The report cited standardized components, documentation procedures, and networked supply coordination. These principles became reference material for later aerospace and nuclear facility programs. Industrial managers described it as engineering by repetition. In naval records, the Liberty ship is often summarized numerically. Average displacement, 14,245 tons. Average speed, 11 knots. Average service life, 4.3 years. But these figures only illustrate the framework of a broader transformation. It marked the moment when mass production supplanted individual craftsmanship in naval engineering. Archival correspondence between Allied logistics officers reflects quiet acknowledgement of this transition. British observers in 1945 noted that the US had converted steel and time into strategic reach. German analysts, interrogated after the war, admitted defeat in industrial tempo rather than technology. Their U-boat commanders reported that the ships multiplied faster than we could sink them. Such assessments underline the program's true significance. Industrial arithmetic had replaced naval rivalry. By 1950, the remaining Liberty ships began gradual decommissioning. Some were scrapped, others entered reserve fleets at Suisun Bay and the James River. A few were retained for emergency sealift capacity. Among them, the SS Jeremiah O'Brien and SS John W. Brown survive as museum vessels. Both remain operational under preservation status, representing the endurance of functional design. In retrospect, the Liberty ship was never admired for beauty or innovation. Its impact lay in procedural efficiency and reproducibility. It symbolized the conversion of theory into measurable output. From keel to cargo hold, every inch reflected calculation, not craftsmanship. In that precision, America discovered a new dimension of power, industrial time itself. The legacy of the Liberty ship persists in modern logistics. Containerization, modular construction, and prefabricated engineering all trace their lineage to its methods. What began as a toy-like experiment became the foundation of global supply architecture. Between 1941 and 1945, the United States did not just build ships, it built a system. The Liberty ship was its first true prototype.